Next, let's very quickly look at some games. So previously we looked at games which were sequential, minimax, and we did a lot of work over there. Now we look at one-shot games. So the one-shot games are the games wherein you make a move, I make a move simultaneously, and because we both make a move simultaneously, we have the result right there. Funny thing, what is the intelligence over that one? Like a two-finger Mora. So I hide my hand and then I suddenly show you 2 or a 1, and I'm even, you are odd. If the sum of our fingers is even, I won, equal to the sum of the 2 values. If it's odd, you won. So I show you 2, you show me 2, 4, I won, 4 points. I show you 1, you show me 3, you show me 2, sum is 3, you won 3 points. Easy game. So we look into one-shot games. So there are 2 players, and of course they 2 taken both the actions simultaneously. The results are what are called as a payoff. So payoff is how much total score I get and how much score does the other one get. And of course there's only a single output. What do you do immediately? So the output will be called as a strategy. There are 2 types of strategies. The first one, which is a pure strategy. The pure strategy is, this is the best action, take it. So I give the action. Like two-finger Mora, I might just say action 1 or action 2. The mixed strategy is, where you say with which probability that you take the action A. So I say 1 with a probability of 0.3, 2 with a probability of 0.7. So I play randomly. And if you see what I'm playing, and what I'm doing is that I'm taking out actions with the same probability distribution. So there's some intelligence, which is the probability. So that's a pure strategy, and that is what is the mixed strategy. And strategy for all the players is what's of course called as a strategy profile. That says the strategy of all players, which gives me the final outcome, how much do you actually get. So let's get on to a single example of a game, and I mean similar to this. So I say that there are 2 people around over here. The first one is a roll number 1, and the second player is who is called as a roll number 2. These are the 2 players, and I know from my experience that R1, roll number 1 and roll number 2 were caught cheating, and it's my duty to find out who is the culprit. Either R1 would have stolen R2's programs, or R2 would have stolen R1's program. So I need to find out. The evidences are not clear, and therefore I first go to R1 and I say, R1, I know you're a very good student. I've been knowing you for a very long time. Tell me truthfully, did R2 cheat or not? And R1 has 2 actions. R1 testifies that R2 cheated, or R2 refuses to testify that R2 cheated. Then what do? I go to R2. R1 and R2 are in different rooms with 2 different committees. So I go to R2, I say, R2, I look at your face, I look at your previous experience, I look at how beautifully you scored in my last test. I fail to believe that you would have cheated. Tell me truthfully, did R1 cheat? And of course, R2 can testify or R2 can refuse. So R2 says, yes, R1 cheated, you are correct. Or R2 can say, no. I'm not saying that I cheated, but R1 definitely did not cheat. And what happens is that if R1 says R2 cheated, R2 says R1 cheated, what do? Is I award -5 marks to R1 and I award -5 marks to R2. I've got evidence against both of them. R1 said R2 cheated. R2 said R1 cheated. What else am I looking for? On the other hand, things are more interesting when R1 says R2 did not cheat, R1 refused to testify, but R2 said R1 cheated. There's a clear evidence. So R1 said R2 did not cheat, R2 said R1 cheated, and believe me, I am gonna be so angry with R1. There is a clear evidence. I'm gonna award a -10 marks and R2 should have been given a +5 for exposing R1. But I say, okay, I mean, there cannot be marks for exposing. And similarly here, R1 says R2 cheated, R2 says R1 did not cheated. So R1 is innocent and R2 is guilty as proven by R1. And they both say none of them cheated. There was no evidence against each other. So I really have to let them go. But then I look at their copies and I'm really mad at them. I know one of them is lying. I cannot find out who is lying. So I open their copies and I just treat them a bit of a lesson. Next time, don't do something like this. Extremely small. So now the problem is that because I've taken so many tests and every time I do this, R1 and R2 know my tactics. The only thing is they don't know that what the other person has said. So R1 thinks if I testify, what happens? And if I refuse, what happens? So I've asked the question to R1, did R2 cheat? And R1 says, if I testify, I will either get a -1 or I'll get a 0. Okay, oops, I should have done it for R2. So my bad, let me repeat it up. So R1 thinks if R2 testifies, what happens? And R1 thinks if R2 refuses, what happens? So R1 thinks if R2 testifies, if I testify, I get a -1. If I refuse, I get a -10. This one is better. So out of -5 and -10, -5 is better. So if R2 testifies, then testify is a better action. Because if you testify, you get a -5. If you refuse, you get a -10. So testify is a better option. Now, R1 thinks if R2 refuses, so this row, then if I testify, very good, 0. If I refuse, -1, 0 is better. So R1 thinks if R2 refuses, then testify is a better option. So if R2 will testify, then R1 should refuse. If R2 refuses, then if R2 testifies, then R1 should testify. If R2 refuses, R2 should also testify. In both cases, it should testify. So there's no point in R1 and R2 having a cheating on each other. R1 trying to look around, what is R2 doing, because my action depends on his action or her action. So in both cases, testify is better. So R1 decides to testify, and you do the inverse thinking. I'll say that it's symmetric. So R2 is thinking if R1 testifies, then testify is a better option, -5 versus 10. And if R1 refuses, 0 is better than a -1. So testify is better. So both testify. Both get a -1. The problem, if we would have done the other way round, let both of them be in a room and said we'll come back after 10 minutes, both of them would have refused. The outcomes are worse than the best outcome possible. But they both have testified using AI and both are going to get -5. I'm happy. I had to give a 10 as a punishment, whether one takes it or both of them takes it, not my concern. This was where I was sad. The problem is of course called as prisoner's dilemma. And this is what is called as equilibrium. It's also called as a dominant strategy. Because you don't have to look at the other one, you could just say without looking at the other one, what did you do? And this one is, so the word equilibrium in games is associated to John Nash, and of course many times we call it as the Nash Equilibria in honor of the scientist. Won a Nobel Prize. When will I win it? Anyhow, so now we look into a pretty much more interesting game. So let's see if we could complexify it up a little bit. So the story goes that there are two companies, A and B. Is the coronavirus pandemic going on, and these are two movie makers, so they try to find out whether to release their movies in cinema or to release their movies at the OTT platforms. I won't carry the story long, but then finally for some weird reason the payoffs happen to be something like this. So let's say a +10 and a +10 and a +5 and a +5, and let's say a -6 -4 -4 -3, whatever. So it's an interesting game because you see that if both of them agree, then they are at a win. If any one of them disagrees, then both of them are at a loss. So it's good to agree. So it's a wonderful game. You propose to a girl, the girl accepts, both agree, it's a happy married life, both positive. You decide not to propose to the girl is also not interested, you break apart, both of you get better life partners, both of you are happy. The moment you agree, it's good. The problem comes when you love the girl doesn't love you, you disagree, then you make her life a hell, or the girl loves you and you don't, then the girl makes your life a hell. So just a simple game. So now if you do say, if you use the same technique, you say what if B says cinema, then for A cinema is a better option, but if B says OTT, then this one is a better option. So there's no dominant strategy, and because there's no dominant strategy I cannot use my technique. And similarly with the other one, there's no dominant strategy. Suppose I give a time delay and one decides and let the other one follow it up. So B somehow decides cinema first, and then A decides. So then it decides whether cinema or OTT, this one is better, +10, +10. So they both come up over here. So if first B plays and then A plays, they both come up over here. Which is the best option? Wonderful. Let's do it the other way around. So what if B first decides out of these two, OTT, and then A decides, then they come around over here. That's also very good. It's not the best, but it's still better. What if both of them play it randomly? A decides cinema and B decides OTT. So now this is the one which is bad for both of them. But now what A will do is, suppose it's a sequential games, you can change your decisions later on. So A says, if I change my decision, I go to this one, and then what will do, A will request B to change its move and B will happily oblige. Or the other way around, B will change its move and A will happily oblige. So these two are what are called as the equilibria. These are equilibrium because if A changes a strategy, it gets worse. -6 versus 10. If B changes strategy, +1, +10, -3, it gets worse. So nobody will change their strategy. They're happy. The moment you change your strategy, you're doomed. Unfortunately, there's also an equilibrium. So I talked about equilibrium, that nobody will change their strategy. I didn't talk about the best equilibrium or the bad equilibrium. So there are two equilibrium, one is better, the other one is bad. So no matter where you start off, if you can change your moves, you will get into either of these equilibrium. If you get here, either A will change here or B will change here. If you get here, either A will change here or B will change here. However, if you are at the equilibrium for these games, you'll never change. And John Nash is particularly credited to proving that every game has at least one equilibrium. And because every game has at least one equilibrium, you can find that out and play it beautifully.